In this video, we're going to look in detail at variables. Variables are something that we've already mentioned a few times in previous videos, but never really looked in detail at them. In particular, we're going to extend our knowledge of variables from fields and parameters to add local variables as well. So what is a variable? Well, in simple terms, a variable is a name given to a small piece of computer memory. And you're probably familiar with the idea that a computer stores bits in its memory. And by giving a variable a data type, we have a way to interpret what those bits mean. So we interpret the bits as meaning a value from the range of the data type. So the data type might be integer, so the bits mean a whole number, or the data type might be Boolean, in which case the bits mean either the value true or false, and so on. So one way that we can visualize the memory of the computer is to say that we'll give names to some of its memory locations, and those names will be variable names. Each variable will have a data type, and then that allows us to, for instance, interpret the value stored in the memory location called answer as being a character, in this case the single character y, or perhaps the value stored in the memory location called ready, as it has a Boolean type, might contain the value true, and so on. Now, as the name suggests, we're often interested in changing or varying the value stored at a particular memory location. And typically we make a change to the value by using an assignment statement. And an assignment statement can be viewed as a copy operation. So if we look at the example on this slide, we want to make an assignment from the variable z to the variable y. And if the state of the memory before that operation, when it's performed, is that y currently contains the value 4 and z currently contains the value 5, then the assignment operation results in the value in memory location z being copied into the memory location y. So now we have two copies of that particular value, one called y and one called z. We've seen a couple of sorts of variables so far. We've described fields as being one sort of variable. Now, fields provide an object with what are called its instance variables. And instance variables are persistent. In other words, they store values throughout the life of an object. When an object is created or constructed, we use assignment statements inside the body of the constructor to assign initial values to the instance variables. In other words, the variables defined by the fields. Fields are accessible throughout the body of the class. So no matter where it's defined inside a class, any of the methods, any of the constructors are able to both read and write the values of those fields. We often use the word private in front of the definition of a field. In fact, that's something that we'll do consistently throughout these videos. And what that does is it limits accessibility of those instance variables to purely the body of the class. Nothing outside the class can gain access to those variables other than through things like access methods and mutator methods, or getters and setters and various other methods. So that provides for something called encapsulation, which really means that an object maintains complete control over the values of its instance variables. And this can be a very important feature of class definitions because it allows an object to prevent inappropriate assignments being made to its variables. So using the visualization of objects that you'll be familiar with from BlueJ, we might characterize the instance variables of a ticket machine as looking something like this. We have an object. Inside that object, we've got three instance variables: price, balance, and total, all storing various integer values at some point within the lifetime of this object. Now, those variables come into being when an object is created, and those values can only be changed via the mutator methods defined inside the class, explicitly because we've defined those fields as being private. So the ticket machine class provides encapsulation for the data inside a ticket machine object. And those three instance variables will persist throughout the life of the object. So they'll still be there when methods are called, when methods finish, when another method is called, and so on. So that's not the same as saying that the values cannot be changed. They can clearly be changed by mutator methods, but those variables stick around for the whole lifetime of the object, and that will be in contrast to other types of variables that we'll discuss in a moment. Another sort of variable that we've seen so far is parameter variables. And parameter variables are temporary variables. Unlike instance variables, parameter variables only come into existence at the point at which a constructor is called or a method that defines those parameters is called. And as soon as that constructor has finished, or as soon as that method has finished, those parameter variables are discarded. They're thrown away. Now, parameter variables are explicitly designed as a way for values to be received into a method or a constructor. So they receive values from the caller of the method or from the caller of the constructor. And the value of a parameter can only be accessed from inside its defining constructor or method. So that's in contrast to instance variables. Remember that an instance variable can be accessed from any method or any constructor defined inside the class. A parameter to a method, for instance, can only be accessed from inside that method. It can't be accessed from any other method within the class. So let's look at the mechanism by which a parameter might receive its value from a caller. Here we've got a ticket machine, and we're in the process of calling the insert money method on that particular ticket machine. So some other part of the program has called insert money on this particular ticket machine instance, and it's passing the value 500 into the insert money method. Now, because we're now going to be dealing with two different parameters, the parameter at the call and the parameter at the receiving method, we need distinctive names for those two parameter positions. So what we say is that the value in the call, in this case 500, is the actual parameter value. So actual parameter is what we call the value in the call. And the receiving variable is what we call the formal parameter variable. So actual parameter in the call, formal variable, formal parameter in the receiving method. So as the call takes place, then that actual parameter value is copied into the receiving formal parameter. So it's a similar kind of copy operation as we saw with assignment, and then that formal parameter will now contain the received value, and that parameter value can be used inside the body of the insert money method until the end of the method is reached, at which point that formal parameter amount will be discarded, and any future calls to the insert money method will result in a completely new version of the formal parameter being created that will receive its actual parameter value. That'll get used, and again that formal parameter will get thrown away again. So parameter variables come and go, come and go, come and go throughout the lifetime of the object, again in contrast to those instance variables which persist throughout the life of the object. So that's fields and parameters. We've seen those in previous videos. We've already discussed those. We're aware of their existence. Let's look at a third sort of variable that we can make use of inside a Java program. So methods and constructors are both able to define what are called local variables. A local variable is defined inside the body of the method or constructor. So inside the opening curly bracket and the closing curly bracket, nested inside the body of the method or the constructor. And there's an example on the slide of how we might define a local variable, in this case an integer local variable called money left, and we're assigning to that variable the result of subtracting the price of a ticket from the current balance. In other words, we're calculating how much money is left over when one ticket is issued to this customer. For instance, they might then want to be able to print another ticket and so on, but we're calculating the extra money that the customer has inserted before a ticket is printed. Now, one thing to pay careful attention to is that we never write public or private in front of the definition of a local variable. Words like private, for the purpose of encapsulation, are reserved for field definitions. So we never see those inside the body of a method or a constructor. Why do we have local variables? Well, they're typically used as helper variables for temporary calculations inside the body of a method to help it do its job. And they are short-lived. So again, they come into existence when a method or constructor is called, and then as soon as that constructor or method finishes, those local variables are thrown away, their values are lost, and any future calls to the constructor or method will result in a completely fresh version of that local variable being created. So let's look at an example of how we might make use of a local variable in order to write a particular method. Suppose we want to give the ability to a customer to have extra money returned to them from the machine. So they put some money in, it's too much for a ticket, they printed the ticket, and now there's excess money in the machine, we want them to get a refund. And so the machine is going to return the amount of the refund from a method. But if the money is being returned to the customer, then clearly we need to set the balance to be zero because that money is not going to be in the machine anymore. So this method has two interrelated tasks to accomplish that are potentially in conflict with one another. We want to return the value that's in balance, but we also want to set the balance to be zero. So how can we write this method without losing the value of balance? Let's look at one unsuccessful attempt to write a solution to this method. So here we've got the header that says that this method is called refundBalance, and it's going to return an integer, in other words, how much the balance is, how much money is owed to the customer. And inside the body of the method, we've got that attempt to return the money to the customer, so return balance. And then immediately after the call to return balance, we then set the balance to be zero because the money is no longer in the machine. Now, on the face of it, this looks entirely logical. We're returning the amount that's excess and we're setting balance to be zero. The problem is that the language does not allow us to execute any statements after a return statement has been executed. And the compiler will notice that there's an assignment after the return statement and prevent the source code from compiling. It simply won't allow this to be written. So let's look at an alternative, which is to put the two statements the other way around. Suppose we were to write the body of the method like this. Now in this case, there's no problem with compilation because the return statement is the last statement inside the method's body. So that's fine. The problem is that we're clearing the balance to be zero, which immediately loses what its previous value was. And so when we then come to return balance, the sequence of statements means that we will have set balance to be zero, and therefore we are always returning zero. We've completely lost what the value of balance was before it was set to be zero. And this is a typical situation where a local variable is going to help us out. So this is the solution that we're looking for. Essentially what we want to do is remember the current value of balance in a new local variable. So we declare a local variable called amount to refund, and we're copying into that variable the current amount that's stored in the balance field. And having done that, we've now got two copies of that value. We've got it in balance, but we've also got it in amount to refund. So we can then zero the balance, and that will have no impact on the amount to refund variable, because all we're doing is we're changing one copy of that value, the balance variable copy, to be 0 and leaving the other one alone. And so then when we come to execute the return statement, the value we're returning is whatever was copied into amount to refund 2 statements earlier. So this is a successful attempt to write that refundBalance method that overcomes both of the problems that were illustrated in the 2 previous unsuccessful versions. Now there's some terminology associated with variables that it's worth you getting to know, and the 2 bits of terminology are scope and lifetime. And these touch on things we've already mentioned, although we haven't used these words. So scope refers to the accessibility of a variable. In other words, which part of the class definition can read and or write a particular variable, be it a field, a parameter, or a local variable, and how long does a particular sort of variable exist in the lifetime of an object. So we say that the scope of a field is its whole class. In other words, any constructor, any method is able to access the value of a field, an instance variable. So the scope of a field is the whole class. And the lifetime of a field is the lifetime of its containing object. So once those instance variables come into existence, as long as the object is in existence, those instance variables will exist. Their lifetime is the same as the lifetime of the object. Now, in contrast to that, the scope of a local variable, and indeed the scope of a parameter, is limited to the constructor or the method in which it's defined. So let's separate those out, parameter and local variable. A parameter can be accessed from anywhere inside the method in which it's declared. However, a local variable has a slightly more nuanced definition, because we're actually allowed to declare a local variable inside any pair of curly brackets inside the body of a constructor or a method. So for instance, we might have an if statement where inside the true part of the if statement we have a pair of curly brackets that mark a series of statements to be executed if the condition is true. We could, if we wish, define a local variable inside that block of statements. And in that case, that local variable would only be accessible from that limited block of statements, not the whole of the method. So when looking at the scope of local variables, we look at the outermost block in which it's defined, and we say that that variable is then accessible from anywhere inside that block. The lifetime of a parameter is the lifetime of the method or constructor. It comes into existence when the method or constructor is called, goes out of existence when the method or constructor ends. And similarly, the lifetime of a local variable is the time of execution of the block in which it's defined. So in summary, Java provides 3 types of variable or sorts of variable. We have instance variables. These are defined by fields. We have parameters, which are designed to receive values when a method is or constructor is called. So those parameter definitions are the formal parameter definitions, and they will receive the values of the actual parameters when the constructor or the method is called. And finally, local variables are defined and set locally within the body of a constructor or method, and they may be defined in quite deeply nested blocks inside the body of a method. Instance variables are persistent, they last for the whole lifetime of the object, but parameters and local variables have a shorter lifetime. They're temporary variables, they're short-lived.